Okay, hi. I thought people might appreciate seeing what's going on here. Uh, what we're doing is getting microwatt to boot a Linux kernel under verilator, and this this is not as easy or as simple as it sounds, um, because um, uh, uh, whilst there is a web page showing that showing how to boot microwatt on an boot Linux with microwatt on an RTA7. There is no infrastructure in place up until now to do that under verilator. Um, so what I've had to do is a number of things, and I'll just go through them. Uh, Let me just expand that. Xterm, nope. Default, medium, large. That's better. Let me see if I can change the font to bold it or something. No, I can't. Yeah, anyway, okay. So the um, the original version of microwatt verilator only basically did UART and TX, UART, TX, and RX, which is a 16550 compatible simulated verilator, simulated UART, which is pretty good. It has automatic detection. Well, not automatic detection, but it can detect, based on the baud rate. But it's also got access to std in, std out, and redirected, so you can actually have an interactive console. Now, the loop here, the main verilator loop, used to be very, very simple. It was while not finished, tick, do the UART, and that's basically it. What I've had to do is I started off trying to compile the Linux kernel into the actual VHDL, and when it got to 60 gigabytes of resident RAM, because it was producing a 512 megabyte Verilog file, I decided that maybe this wasn't a good idea, and instead what to do was, rather than have the VRAM embedded inside the VHDL, which then turned to the Verilog, which then did a whole batch of millions of zeros, bits of ones and zeros. I decided to actually make it possible for Verilator to load the file into memory and to emulate the VRAM from C++ inside Verilator. Okay, so that's what this is about here. When you've run microwatt verilator, giving it a file name to load into memory, to mmap, and then open mmap and then memcopy over, it will go, we're in memory served BRAM simulating mode. Let's look out for the read enable and actually set that BRAM data out is what you're reading, and then there's the write. If the write enable there, do the write. Okay, all right. So all good. All good there. It turns out that the so 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 that initially initially loaded. So I was able to run the hello world program, and I should be able to do that down here. And now /microwatt verilator hello underscore world hello dot bin. loading, and there we go. It's down here. We can see. Now that's given it from the command line. Microwatt it works. Yeah. Alright, so that's the thing, and let's just stop that. And to show you that it is actually command line, let's now do the micropython firmware.bin. You don't give it the hex file, you give it the bin file. Micropython v1.112. Way off we go. 2021 6. Come on. Alright, now there is a reason why it's running this slowly. Well, actually, several reasons. 7 plus 5, return. 12, yes. It's dreadfully slow, isn't it? There's two reasons why that. One is that we're actually doing the GTK wave trace. I put in -mice trace mode. So that's creating a microwatt verilator. That very short run from verilator created a 3.8 gigabyte GTK wave VCD file. And the second thing is that, as you can see from here, bram.dump. As you can see from here, I'm actually doing a memory read and write dump thing. So every read and write to that BRAM, you get a debug print message thing to a log file, which is how I was able to tell what the heck was going on. But it does mean, I mean, this is fantastic. You know, you can see all of the memory traces, every single read and write that's going to that BRAM. So that's how I was able to check, is this at all working at all? Now, so there's two things making it horribly slow. So let's do a make clean. So %1 minus trace, and take out the trace. Make microwatt verilator. And snooze. And here's the trace I prepared earlier. And this was just seeing what's going on here. Now you can see right, this here is the UART 0, UART 0, the 1650 wishbone address. So you can actually see when it's reading and writing to the 1650 UART. And if I span out a bit, not too much, and we have a look at enable, let's pan out a bit more and have a look at the pads. Should actually be able to see, where are you, UART and receive and thing, me pads. They're around here somewhere. I just dumped all of the signals. Serial out. There we go. There's the serial out signal. Yeah. There we go. This one, serial underscore out, is the actual UART serial console in binary, which is then picked up by UART verilator.c, which has its timers and tracks the things and actually turns it into actual ASCII characters that you can see on the screen. So, anyway, that's completed. Now let's move this out the way. But I can also, oh, by the way, I can also track which memory address is currently being executed. Addr. I think it's that one. Addr. Yeah. So Addr 16C0. I think that's the one A. So it's one of these anyway. So you can see the BRAM data out is what the instruction instruction or data is being read. And at some point I did have I took note of which ones were the wishbone data bus. Yeah, these ones I think is the mouse over. That is the wishbone data in this lot here. Whoops. These ones the wishbone data, and this one's the wishbone address. So if anything that gets read on there, you can tell which ones are instructions and which ones are load and stores. There's the address. There's the address one. I'm sure that's it. 905. Yeah, this is executing the Linux kernel. This is from an earlier thing. Here's one I prepared earlier. Yeah, and if you look at this one, whoops, zoom in, there, zoom in, not out. C00210. That's the address for the. If you look in the microwatt DTS file, you'll see that's the address of the UART. So it's all there. It's just one hell of a lot of detail. I think. Okay, so let's rerun that micropython thing, and it should not be doing. Yes, it isn't doing the GTK wave trace at the moment, but it is still doing the BRAM dump, and that's okay. All right, so that's a 7 plus 2, 9. It's a tiny bit quicker, but at least it's not producing 3.8 gigabyte files. Now, let's run the 1382. Let's run the right. I'm not going to run it yet, but what I'm going to do first before doing it is I'm going to show you the modifications I made to SDRAM in it to effectively turn it into a standalone mini BIOS. All right. So the first thing I did was I added a new sysreg BRAM info. Now this syscon, I have no idea what it is, but basically it appears to be some sort of way of the hardware being able to inform the software of what its capabilities are. And I decided to add an extra register to that, which would allow me to specify a boot address that I wanted the RAM to be at. To start if you didn't discover an SPI or whatever, blah blah blah, and that's done here. Okay, so if it has a sysreg, if BRAM is built-in BRAM is available, and the BRAM is what we're pretending is simulated, and we're setting up 256 megabytes of simulated BRAM. Normally, your block RAM would be like 4K, and it would be barely enough to hold the initial bootloader, and that's what was supposed to be initialized by in the FPGA, so that when you upload your RTA7 thing, you're uploading a mini BIOS which does the early boot initialization, initializes the DRAM, initializes the console, etc., and the PLLs and blah blah blah. It's all standard stuff for embedded systems. You have to have this boot procedure, but we're just expanding it and overloading it. So instead of a 4K BRAM, we've got a 256 megabyte BRAM, and consequently we can actually load the Linux kernel into address not x6 not blah blah blah, but we need a way to jump to it. Okay, right. So and that's what this is about. Okay, so having done that, we can now load both of those into memory. We can load that early bootloader, basic BIOS, into memory at address 0. We can load DTB image.microwatt, Joe and Ben Harrismith's and Paul's microwatt 5.7 kernel with Paul's build route, and we can now execute it. There we go. Off we're going. So it's telling us loaded the SDRAM init.bin, which is that standalone program here. So it's loaded that at address 0, and its size was not x2680. Its size was 9856 bytes. And we've also loaded the DTB image.microwatt, which includes the init RAM disk, which contains build root. And it's saying booting from BRAM at 06000. Ooh, and we're getting a Z image starting. Ooh. At 06000. Now I'm going to go and grab a comparative web page whilst that's running, which you can see here, and it's basically going through this process. So that it's grey on grey, unfortunately, on this page thing. So here, this welcome to microwatt. You can see we have the same equivalent. Welcome to microwatt. Rather than being in the RTA7, which says SOC features UART, DRAM, and SPI flash, you can see our SOC features is just UART and BRAM. It's saying BRAM size is 512 megabytes, and I've set the boot address in the syscon to 06000, which 0x6000 matches that DTB image address. So it's now decompressing, and we can actually, sorry about that, with the mouse in the right screen, sent to, we can actually see that dump process. You can see this is actually witnessing the Linux kernel early boot process was decompressing out of decompressing into memory ready to execute. It's so exciting and taking forever. D in, D out. So here we have, that's clearly reading instructions into the cache, the emulated cache, woot. And that's D out, that's your store. So that's your load of the sections, and that's storing. And this is going to take forever because it is running, it is a simulator, Be nice to have some progress notification here, some dots, wouldn't it? But I mean, normally, this would be done in milliseconds. Decompressing a Linux kernel doesn't normally take this long. You can see it's doing it one byte at a time. You can see each of those writes is doing. Whoa, that's painful. And see the write select 3, see 1, 2, 4, 8. So it's going write that first byte, Right, that second byte. Right, that third byte. Right, the fourth byte. Right. Oh, 6, 7, 8. Oh, that's really painful. But you can see it's done 0, 2, 0, 0, 2, A4, EA, 80, 01, 84, EA. There's probably some instructions somewhere being written to memory by the decompress. How far has it got up to so far? What address has it got up to? Not. Now that's offset down by 3 bits because it's a wishbone address, but it's a 64-bit wide. So no thing. Right shift by 3. Whoops. Hex. Here, I want that in hex. 929B28. Ooh. And if we look over here, we have 92689. I just wonder how long those things, if we can estimate how long it's taking. Hex brackets 3. Yeah. Nox thing. 930E90 minus Nox 929B28. 29,000 bytes. 29,000 bytes divided by, let's say it was 30 seconds that it took us to notice that. So it's 1,000 bytes a second. Oh, wow. Right, we're going to be here a while. Yeah. 1,000 bytes a second, and how many have we got to do? Size 0x327018. 3305 seconds. That's going to be an hour. Holy cow. So this is why people don't do simulations of Linux under verilator. Let's leave this to chew over and maybe come back later. And think, oh, I can pause the video, can't I? Yeah, I can pause the video, so I'll do that, and I'll restart it later in an hour. Go and watch some Mythbusters episodes, I think. All right, see you in a bit. Hello, I'm back. I decided I'm going to end this video, and I'm going to look at options to do an uncompressed kernel. I'm just looking at this, and it says that you can run with an uncompressed image. So I think that will be the same thing to do, rather than have it run for an hour. Memory is cheap, but processing power in this case being 50 to 100,000 times slower than real time, it's probably a good idea to just go with the flow, shall we say. All right, so thank you very much.